Hi, good morning, everybody. Let me remind you, this Friday will be test number 1. Test number 1 covers chapters 1, 2, 3, appendix A2 and A4. I've gone through every practice problem set for this material on test number 1. You'll need to bring a calculator that does scientific notation. We've done that both in the classroom and in the lab, but look at that one real quick. And bring pencils or pens. I write with a pencil and eraser. I will try, traffic and Dr. White permitting, to get here maybe 15, 20 minutes early. If you have any last minute questions, come and ask. The best way to study for the test, do the practice problems. If you've done those, look at the notes, you're in good shape. If you missed anything, don't forget, I'm a YouTube star, so you can go to my CHEMI 1105 YouTube channel and see me. And the back of your head, some of you. All right, it's time for the world famous review for the next test. In this case, it's test number 1. Everything you see on the screen here is on Blackboard, and you can download it. All right, first of all, you should know when we start out, the 4 branches of chemistry, you should at least know one. The best is organic. I'm an organic chemist. The others are physical, analytical, and inorganic. I never liked inorganic. Next, I talked about matter. And matter is anything that has mass, weighs something, and occupies space, which means everybody in here is made up of matter, because you're occupying space and have mass. All right, now, we've gone through the chemical symbols. You should know the chemical symbols. You see me use the periodic table in class, the green one, which has no names on them, and that will be on your test. So make sure you have learned those by now. Now, we went through the 3 states of matter. And, oh, why not? Let's have some fun. Class, the first state is, begins with an M. Everyone. Let's get together, fire up. The sun's out, there's no 20 inches of snow on the ground, it's not ice. First state of matter. Solid. Thank you. Next one. Well, you're falling down. Last one, pick it up. Gas. Thank you. And you should know a solid has definite shape, definite volume. A liquid has indefinite shape. That means it takes on the shape of the container, like my water bottle, but it has definite volume. And a gas has indefinite shape, indefinite volume. And you should know those. All right, now when we talk about matter, there are different types. One is a pure substance, and a pure substance consists of either elements or compounds. My ring hopefully is a pure substance, gold. And the water in my bottle over there hopefully is a pure substance. It's a compound, or I'll use the term compound interchangeably with molecules. And there you go. Now, the other type of matter we call mixtures. And later on, you'll also hear me use the term solution. And right now, you're sitting in a mixture. That's when you have 2 or more different substances or material mixed together where neither one interacts. And there are 2 types of mixtures you should know. Homogeneous. That's when it's the same throughout. And luckily, we're all sitting in a homogeneous mixture here, because if I move over here, I'm not going to say, oh, no oxygen, I'm dying. No, luckily I don't do that. Sorry for that awful joke. No, I'm not sorry. It is pop out. And heterogeneous, they're not the same throughout. 2 different layers. If I took and put sand in my water bottle, I won't, but if I did, the sand would go to the bottom, and you'd see different layers. It would be heterogeneous. For those of you who've seen oil vinaigrette dressing, after you shake the bottle up, put it on your salad, put it down, look at it 10 minutes later, you'll see two separate layers because it's heterogeneous. Now, there are different types of properties of matter. One is physical property, that's something you can observe. The other is chemical property, which tells you how it changes. And I'll never ask you what's a physical property or chemical property, but I might ask you to give an example of one. An example of a physical property is, well, my shirt is a yellow color or butter color, whatever you'd like to pick. My sisters always say, I don't know my colors on any basis. But, and a physical, chemical property, the material in this bottle, water, won't burn. In fact, firemen use it, and women too, let me not discriminate. Fire people, I guess they call them that. But anyways, they use that to put out fires because a chemical property of water is it doesn't burn. Now, gasoline, do not try this at home or anywhere else, it does burn. It's flammable, and that's a chemical property. Now, when we talk about changes in matter, there are two types, physical change and chemical change. An example of a physical change is when something changes in the state of matter but doesn't change its composition. An example would be if I had a glass here with ice cubes, or just ice cubes in it, just ice cubes in a glass, and I put it here, and at the end of the lecture you'll say, oh, where'd the ice cubes go? They melted. And that goes, water goes from a solid to liquid, and that's a physical change. Another one, if you boil water or any liquid, you're going from a liquid to a gas. Those are physical changes. Chemical change is when something changes its chemical identity. It changes into something different. An example of that would be, let's think, oh, when you step on the gas in your car, or if you're with someone in their car, they step on the gasoline goes into the engine and undergoes a chemical change to carbon dioxide, water, and heat, and the heat makes your car run. And another example of a chemical change, not to get too personal, but if you had breakfast this morning or dinner last night, and once you swallowed your food, it went in your stomach, it underwent a chemical change. It changed to something else that your body can use to keep you alive and healthy. Now, went through problems in class, and I think in the lab too I did problem set, where we did the different changes in temperature. You should know how. I give you an example. If the temperature in this room is 25.7 degrees C, what's its temperature in Fahrenheit? Use the top formula. Now, if I give you the temperature of my house right now when I left was 64. I keep it cool because I enjoy it that way. I got my winter fur on. But anyways, I asked what's the temperature in Celsius, you'd use the second one. And finally, if I said the temperature in temperature of a gas is 101 degrees C, what is it in Kelvin? You'd use the third one. Now, some instructors will say if the temperature is so much degrees F, what is it in Kelvin? That's not real world. I've never had to do that, so I don't do that. You just have to know how to use each formula. Now, there's an important thing. On test one, it will say, please use proper significant figures for all calculated answers. Let me remind you, in these three formulas, 1.8, 32, 1.8, and 273 are all exact numbers. That means they do not play a role in figuring significant figures. So if I were to put in here 101, three significant figures, we'll cover that in a second, my answer should have 3. Same thing with any of these. And The last one is addition, which I wouldn't, haven't covered, but we'll get to that eventually. We need it. Now, let's take a detour. If you go to the lectures folder and school Blackboard, scroll down, you'll see important test number 1, important information. Let's open it up. These are things this page, as you see it, plus afterward will be a page with the periodic table, will be in each test booklet or stapled package. And you don't have to memorize those formulas. In the past, I had students memorize them, but I changed my philosophy, and you don't have to memorize them, but you do know how to use them. And I'll cover the other stuff in a little while. Now, we talked about, notice I say I talked about you were polite and listened, but we practiced. And that was scientific notation, which is a number that's the first part is from 1, never less than 1, never more than 9.999, whatever, and times 10 to the n. If the number is greater than 10, 10 is positive. If it's less than 1, n is negative. I say 10, n is positive, it's greater than 10, n is negative, is less than 1. Between 1 and 10 is 0, but I've never put that on a test, so you have my word on that, I won't. And you should know how, here's a number, take it, write it in scientific notation. Here's a number in scientific notation, write it in numeric form. We went through that in class. And practice that in the lab too. Pure compound. Next, I talked about significant figures. There's certain rules. All non-zero numbers are significant. Lead zeros are never significant. Confined zeros are significant. Trailing zeros and no decimal point are never significant. And trailing zeros with a decimal point are always significant. And we went through examples. How many significant figures are in a certain number, and you should know how to do that. We talked about rounding off. How do you round off? You use, if the first digit to delete is 4 or less, you drop it, and everything following that when it's past the decimal. Or replace it with zeros if it's greater than 1. And if the first digit to lead is 5 or greater, drop it, and everything that follows, if you're past the decimal, you'll replace it with zeros. If it's not past the decimal, I should have that on there, I don't. And increase the number in front, the last digit to keep by 1. And we've went through examples like this. Now, when you do a mathematical operation in this class, that will either be multiplication, division. I didn't ask you to learn addition yet. I'll do that later when we get to it, next chapter or two. But for this test, you should know multiplication and division. The number you get your answer should have the same number of significant figures as the number that you're multiplying and dividing that has the fewest significant figures. I'll say it again. The number that your answer should have the same number of significant figures as the number you're multiplying or dividing that has the fewest significant figures. So if I were to do the following on a test, and the question is, what's the correct answer using proper significant figures? We all know that 2 times 2 is 4, but that's one significant figure. So multiplication How many significant figures does this have? Ooh, good question. I'll give you 1.8 seconds to figure it out. Time's up. 2 is significant. All zeros past the decimal point. It has 4 significant figures. I come over here. How many significant figures? Non-zero numbers are significant. Zeros past or at the end with a decimal R. 1, 2, 3. 3, which is the lower number. Ooh, tough one. Hope we all pick 3. Therefore, 4, but that's 1. How do I get it to 3? 3 significant figures. And that's how you do that. We went through that this last week in lab. All right, exact numbers. Those are numbers that don't play a role in the rounding off or determining significant figures. An example, the 1.8 and the 32 and the 273 don't play a role. And you just use the degree C. Now, when it comes to, for the periodic table, there are certain families, columns you should know. Not counting hydrogen, but the first column is called the alkaline metal. And if I ask on a test, give an example and a chemical symbol of an alkaline metal, what do? You look at there and say, oh, I'm going to pick Dr. White's favorite potassium, which is K, or you could have put sodium or lithium. There are others, but I only asked you to learn those 3. If I ask the next column, alkaline earth metals, I ask, give an example of an alkaline earth metal. Look there, the only 2 I asked to learn, Mg, magnesium, Ca, calcium. We come all the way over here, the second to last column on the right, I got it correct. And those are the halogens. And if I ask, give an example of a halogen, I'm going to pick my all-time favorite because I work with it, chlorine. And that's Cl. You could have put fluorine, bromine, or iodine too. Those are all good choices. Those are halogens. And the very last column are the noble gases. And you know I picked on krypton a lot this semester, but let's pick one of my favorites because I work with it a lot. Ar is argon. If I ask you to give an example of a noble gas, it's the column, the family, all the way on the right. Next, I talked about atoms. Atoms are the smallest particle of an element that has all the properties of an element. And I have it down there, but let's skip Dalton's atomic theory, which really said elements are made of atoms. I don't think I put any questions on that. I gave it away. But anyways, when we talk about atoms, they're made up of subatomic particles. I think I already burnt you out on class participation, so I won't make you suffer. I'll do it myself, and Dr. White. Oh, that's hokey. But anyways, what are the 3 subatomic particles you should know? Electrons, protons, neutrons. You should know an electron has a negative charge. A proton has a positive charge, and neutrons have no charge. And next, you should know that the nucleus is the center of the atom. And the nucleus, we have protons and neutrons. How do we know that? You should be familiar with Rutherford's gold foil experiment. Warning, fancy word time, elucidated the components and the structure of the nucleus. Elucidated means figured out. So he figured it out, and by his experiments with gold foil, they were able to figure out that the nucleus is very dense and contains protons, neutrons. Yeah, you should know that, it's very important. And you know who was the assistant who helped them do that experiment? Some guy named Geiger. I don't know why I think of that name, Geiger counter. Yep, the same guy who invented the Geiger counter. You don't know what a Geiger counter is? When we get to nuclear energy, we'll talk about this. Next, I talked about important aspects of atoms. First one is atomic number. The atomic number equals the number of protons by definition. Since all atoms have a net zero charge, it also equals the number of electrons. And if we go to our periodic table, if you look at the upper corner, on this one it's on the left, on mine it's on the right, it's always the upper. That number is the atomic number. If you notice for oxygen is 8, and that tells me I have 8 protons and 8 electrons. If I look at another one of my favorite, carbon, and if you look at carbon, it has an atomic number of 6, which means it has 6 electrons and 6 protons. And that's a skill I highly recommend you know. Now, if the nucleus has the protons and the neutrons, where the heck are the electrons? They're in the electron shells. And the electron shells, you have subshells. And when we have the electron shells, the first question is, what's the name of the shells? And they're very hard. Shell 1, 2, 3, and 4. And how many subshells does each shell have? Well, you look at the chart here. Shell 1 has 1 subshell. Shell 2 has 2 subshells. 3, 3, 4, 4. Now, remember, you start, when you look at that table, shell 1 is the lowest energy, and shell 4 has the highest. So when you go down, you're going to higher energy. Now, Mother Nature likes to put the electrons first into the lowest energy shells. And then we have subshells. Notice I cut down and only have 2 there, S and P, because it's a test. In my class, that's like that. No, remember, don't play my gift. You only have to know up to magnesium how to do electron configuration. And let's go over here, And if you look at the important information page you'll be given on test 1, we'll have the electron shell chart and the subshell, and also a little thing to remind you, electron configuration statement, how many electrons an atom has, each of its subshells. Remember, subshell is both a number and a letter, like 1s, 2s, or 2p, and you use only numbers and letters. That will be given to you. In the past, I used to make students memorize this. I have changed my opinion on how to do that about a year ago. And the electron configuration is, where are the electrons? You always fill them in the lowest shell and subshell until you fill it up, then you go on. Let's do one for fun. Who's they are? Now you know this. We look at, if I were to ask, do the electron configuration for magnesium. Let's look. First thing you have to know is the chemical symbol, Mg. Next thing you have to know is its chemistry. Actually, you don't have to know that, but that's the way it goes. And next, you have to know how many electrons. For electron configuration, we're looking at all the electrons, and magnesium has an atomic number of 12, which tells me it has 12 electrons. Now, I'm going to give you a little chance to have some fun before I do. And given this information, why don't you try and do the electron configuration of magnesium? Have fun. Good time-wise, too. Remember, keep your eyes on your own test. Oh, one thing on Friday, I will be asking you that if you have a smart watch, please take it off and put it in your pocket or your backpack or your purse or whatever, because I've caught students cheating using that. It's quite obvious when a student cheats even with that. So. All right, looks like everybody's just about done. Let's do this. Now, how do you do this? You start with the first shell that's the lowest energy, that's shell 1. And its subshell, it only has one, the lowest energy. Remember, in all these charts, this is lowest, going down as highest, is S. How many electrons can I put in S? 2. So I'm going to do that. Now, how many subshells does 1 have? Shell 1. 1. I filled it up. Well, I have nowhere to put any more electrons in shell 1, so now I go to the next lowest energy level, which is shell 2. And the first subshell of shell 2 is 2s. And I look at that and say, how many electrons can I put into it? Well, 2. I want to do that. Well, I still got 8 more to go if my math is correct, and I believe it is. How many subshells does 2 have? 2. The first one is S. What's the 2s? Next one is 2p. Now, how many electrons can I put in any p orbital? 6. Well, I've got 8 to go, so I'm going to put 6 in there. 2 plus 2 is 4, plus 6 is 10. Am I done? No, I have 2 more. How many subshells in shell 2? Well, if you look up there, it says 2. Have I filled them up? Yes. So now I have to go to the next shell, which is 3. And what's the first subshell in 3? 3s. How many electrons can I put in there? 2. How many do I have to go? Oh, good look. 2, and I'm done. And that's how you do it. And for my secret agreement and gift to you, you only have to know how to go up to magnesium, which means you have to know how to go up to magnesium. And that's how you do it. Now, there's another more important type of electrons, and those are called the valence electrons. And you should know that the valence electrons are the outermost electrons of an atom. They're also the most important because those are the ones in every chemical bond. Should I scare you? Yeah, I'll scare you. Look at your skin. Take a look, touch it if you want. And the atoms in your skin are held together by chemical bonds, and the electrons involved in those chemical bonds are the valence electrons. And you say you hate chemistry. If you hate chemistry, your skin will fall, but no. But anyways, those are the most important electrons, in my opinion. They're the outermost. Now, how do you determine how many valence electrons does an element have? You look at the periodic table. Well, I have this slide up. The maximum you can have is 8. You put down 10. and my eyes see it, they don't even go through the brain, they go right to my hand with the red pen, say, that's wrong, then I start laughing, because you can only have 8, so don't put down more than 8 ever. And let's look at my periodic table. And for test 1, I already asked, I'm going to have my favorite element. How many valence electrons does carbon have? We have to know carbon is C, where it is. You look at the top, and you see the number 4. If you don't know your Roman numerals, notice I put the numerical number, because they don't teach you. You haven't taught Roman numerals in schools. How many of you people did not learn Roman numerals in school? The rest of you know it? Well, you can use either one. Last class, more of them didn't know, but anyways, maybe they went to a worse school than you did. But if I ask, how many valence electrons does neon have? Time's up. Hopefully you know neon is Ne. It's a noble gas. Look at the top and you see the number 8. And I'll do one more. Oh, let's do lithium. How many valence electrons does lithium have? I see everybody looking in the right part of the periodic table. That makes me feel good. Thank you. And we look lithium, which is an alkali metal. It's the first column. We look on top, and it's the number 1, so it has 1 valence electron. And that is everything you need to know for test number 1, other than you need to know your name and how to write and print it. And let's do one other thing while we've got this going. Most of you have a similar calculator, and if you have any calculator problems during the test, let me know. I will help out. I also have 2 extra calculators in case yours dies, which does happen. These are solar, so they won't. All right, if you look right here, you'll see something missing. And I'm going to push the second button and see on the blue on above it says psi ENG. I'll put that. All right, come on. There we go. Didn't push it hard enough. And I'll screw over till it's underlined SCI. I'll hit enter. I'm now in scientific notation. Now, in this calculator, most of them are similar. To multiply 1.50 times 10 to the third, second key, double E, on above, and then 10 to the third, times, 4.44, times 10 to the minus fifth, blue, double E. Now, remember, minus in exponent numbers on a calculator is here, not that one, that's for subtraction. So I'll push that, and I think I said 4 or 5 I did. And you'll notice I got 6.66 times 10 to the second, and I had 3 and 3 significant figures, so that's how you do it. And if you have problems with your calculator on Friday, come early, and I'll help you out. All right, how many of you would like me to do the same type of review for test number 2? Raise your hand. All right, I will. Twist my arm. I will for the next step. All right, how are we doing time-wise? Oh, we got plenty of time. All right, any questions on any material on test number 1? Going once, twice. Let's go to the chapter. That will be on test 2. Let's get back to work. Please be on time on Friday. For those of you who lab tomorrow, don't forget your to-do list, wear proper clothing, your goggles, and bring the lab you did last week. time permits, because I have to teach this afternoon at the other school, I'll try and get the review video up and running tonight. So if you want an instant replay, you can. It's not even summer reruns. Now on Monday, I was talking about the chemical equation. And the chemical equation, which I'll never ask in test, was this material for test 2. I always try and finish up at least a week or so in advance material on the test, so you have time to practice and do good. All right, chemical equation. Is a way for chemists to show in a certain condensed form how different substances react together to form new substances, which we call a chemical reaction. And it's a way of doing it with words or letters and symbols. I'll never ask you what a chemical equation is. Now, there are certain conventions. First of all, you should always use the correct formulas, and I'll talk about that in a second. When we look at a chemical equation, we have an arrow. The arrow has a tail and a head. At the tail, you always have the reactants, which, coming from industry, you've heard me say this, but I'll probably use this term more than reactants. The starting materials. And good habits, Dr. White doesn't change. I'll call more modest starting materials as opposed to reactants, but both. At the head of the arrow, whatever you're making are called the product, or called the product or products if they're more than one. And that's the same for both academic and industrial chemists. The arrow always points to the products, the tail is always the reactants, and the plus sign is like the word and. So A and B react to make C. A and B are your reactants or starting material. C is your product, or product in this case. Now, there's a validity check when it comes to writing a chemical equation. The first thing is, it must be consistent with experimental facts. If I mix A and B together and get D, this is incorrect. That's important. Now, the important thing is conservation of matter. There must be the same number of atoms of each kind on both sides of the equation. Now, let's look at a chemical equation. If I take hydrogen gas, H2, and react it with oxygen gas, and you put a little spark in there, it's real cool, there's a bunch of them on YouTube if you want, you will see water form. You use a little pop, or if you allow it, it explodes, because it's very excellent for heat reaction. But here's the chemical equation, and it's incorrect. Why is it incorrect? Because it's not what we call balanced. And a balanced chemical equation has the same number of atoms of each element involved in the reaction on each side. And let's take a look. How many hydrogens do I have here? 2. Remember, H2, 2. How many hydrogens in water? 2. So far, so good. How many oxygens do I have on this side? 2. How many on that? Uh-oh, only 1. So this is unbalanced. And one of the skills you should have for my class, which will be on test number 2, and also on the final, and I promise that Dr. White it will be, and I have never yet, to the best of my knowledge, ever broken a promise to myself, is You need to know how to balance those. And why is this true? Because atoms of elements are never gained or lost or changed into atoms of other elements during a reaction. So how do you balance a chemical equation? And how many of you have ever been on a teeter totter? You know, and if they're not equal weights on both sides of the children, it goes boop like that, or it goes boop like that, or if they're equal, it's like this. How many of you have ever seen one of those pan balances like that? And if the weights are the same, the pans are at the same height. If they're not, well, it's the same, and I think that's where they came to the term balance, because it's the same on both sides, like a scale, old type scale. How do you do that? Now, you cannot change the formula. This has to be hydrogen, H2. This is the formula for oxygen gas, O2, and this is the formula for water. What you can change is how many. And that's the number in front. And we have a name for that. I just spelled it wrong, because that's one of the things I spelled wrong. I did. I tell you, I was always the first one down the spelling bee. And these are called the coefficients. And the coefficients, I'll never ask you what it is, but I'll use that term, is the number in front. And that you can change. Now, how do you balance a chemical equation? Well, it's sort of like balancing your checkbook, which I never liked to do. My mother was an accountant, and if I didn't balance it, I didn't bother them off by a penny. She'd get upset, and I said, why am I going to spend an hour for a penny? I can live with that. She couldn't. But in chemistry, you have to balance equations. How do you do that? Well, you look at how many at first. I have 2 hydrogen here. How many hydrogen do I have under here? And you're looking at atoms. 2 hydrogen. I have 2 oxygen. And here I only have 1. I need to have 2. How can I get this to 2? Can't change, put a 2 there, because H2O2 is a different chemical called hydrogen peroxide. But I can put a 2 in front. If I do that, now I've got to change some numbers. First of all, I'm going to have 2 oxygens, 2 times 1. How many hydrogens? 2 times 2 is 4. So I now have 4 hydrogens. On this side, I look at, let me do this so you don't think it's the number 20. I have 2 oxygen, 2 oxygen here, that's cool. I have 4 hydrogen, I have 2 here, I need to have 4. How can I change this to 4? Put a 2 there. And now I have 4 hydrogens, and I look at that and say, well, is it balanced? Now you do a check that I like to do. Since I write this stuff underneath, I can say 4 hydrogens, 4 hydrogens, 2 oxygen, 2 oxygen. It's balanced, and I'm happy. And what it really means is you take 2 hydrogen molecules with 1 oxygen molecule, and you make 2 water molecules. Let's look at the following reaction. And the first question I would ask you is it balanced? And how do we know if it's balanced? You look and see how many atoms of each element are on each side, and are they the same? So what I like to do is write underneath 1 sodium. When there's no number in front of an element or molecule, the coefficient is 1. Now here, 1 times 2, I have 2 chlorine. Over here, I have 1 sodium. and 1 chlorine. Are they balanced? No. Because if I have 1 sodium here, that's cool, 1 over there. If I have 2 chlorine here, I only have 1 chlorine there. It's not balanced. By the way, in case you thought I'd forget, you go out to dinner, lunch with me, I'll ask, please pass the NAPO and NaCl table salt. So how do we balance this? Well, I have 1 sodium, 1 sodium. I don't have to do anything there. I have 2 chlorine. How do I get 2 chlorine on the other side? Atoms. I can't change the formula, but I can change the coefficient. And I'll put a 2 in front. And now I have 2 chlorine, but I also have 2 sodium. On this side, I have my 2 chlorine, but I only have 1 sodium. I need to have 2 sodium. So how can I do that? I can't put Na2, that doesn't exist, but I can change the coefficient. And now, let's do a check. 2 sodium. 2 times 1, 2 sodium. 2 chlorine. Ooh, 2 chlorine. Success. And we have balanced equation. Remember, because of conservation of matter in a chemical reaction, everybody's got 2 minutes, hang in there, 90 seconds, in a chemical equation, the number of atoms on one side has to equal the number and type of atoms on the other to have a balanced chemical equation. And if you notice this equation, if you take 2 sodium and react it with 1 chlorine, you'll make 2 sodium chloride. And you can see a neat example of that on YouTube, and it gets very hot, and if you do it wrong, it explodes. But with that, you guys are all twitchy, and I'm going to let you out a whole minute or so. Remember, Friday test, be on time. Also, bring a calculator, pencil, and pen. I have a pen